Hello, and welcome back to the Yawning Theories. Wherever you are, and whatever time your clock may be softly ticking, I'm glad you've decided to spend this little slice of the evening with me. Before we settle in, I'd love to know where you're watching or listening from, and what time it is where you are. Are you curled up under a blanket at 10, resting in a hammock somewhere tropical as midnight hums past? Or perhaps it's 3 in the morning and you're keeping company with owls and quiet thoughts. Either way, you're in good company here. If you enjoy these slow, calming journeys through science and wonder, it would mean a great deal if you tap the like button or gently nudge the subscribe bell. No rush, of course. We've got all the time in the world. Tonight, we're going to take a very slow walk through some very slow science experiments so patient, so deliberate that they make glacial movement look impulsive. From clocks designed to chime once every century to blobs of tar that take years to plop, we'll explore the quiet marvels of scientific curiosity, stretched out across decades, centuries, even millennia. This video is a meditation on time, observation, and the human need to understand things that move more slowly than we do. And if that sounds like a perfect lullaby for the curious mind, then you're in the right place. I do hope this isn't too interesting, of course. The goal is to soothe you towards sleep, not rouse you with excitement about gravitational viscosity. But if you do find yourself staying up just a little longer to hear about a bell that's been ringing since the 1840s, well, at least you'll be learning something. As always, this video is for educational and relaxation purposes only. It's not intended as medical advice, treatment, or diagnosis. Please consult a qualified health professional if you have concerns about your sleep or well-being. Now, take a deep breath. Let your shoulders drop. The science of slowness is ready to begin. Let's begin with one of the slowest, most unassuming experiments ever devised. One that's been dripping along quietly for nearly a century without much fanfare, yet holds a curious place in the annals of scientific persistence. It's called the pitch drop experiment, and it's quite possibly the only experiment in history where missing the moment of action has become part of the legend. To truly appreciate the pace of this experiment, you need to picture a small glass funnel filled with a dark, glossy substance. At a glance, it looks solid. You could poke it and it would feel hard, maybe even brittle, but under the surface, it's moving very slowly, dripping. In fact, 1 drop every 8 to 13 years, depending on temperature and other tiny variations. Blink and you'll miss it. Go on a 10-year vacation and you might still miss it. So, what is this mysterious substance? It's pitch, also known as bitumen, a derivative of crude oil. Historically, pitch was used to waterproof boats and roofs, a sticky tar-like material that could be molded when hot, but would seem solid at room temperature. The key word here is seem, 'cause while pitch appears solid, it's actually a very slow-flowing liquid. That's right, it just moves on a time scale that makes tectonic plates look speedy. The pitch drop experiment was started by Professor Thomas Parnell at the University of Queensland in Australia in the year 1927. Parnell, a physics professor, wanted to demonstrate to his students that some substances we consider solids are in fact highly viscous liquids. So he took a quantity of heated pitch, poured it into a sealed glass funnel, and let it settle for 3 years, 3 whole years, just to be sure it had fully settled and cooled. Then, in 1930, he cut the bottom of the funnel stem and placed the apparatus under a glass dome to protect it from dust and air currents. And then he waited The first drop didn't fall until 1938. That's 8 years of silence, no action, no applause, just gravity doing its patient work on a stubborn material. The second drop came in 1947, and so it continued decade after decade, drop after drop. What's both hilarious and endearing about this experiment is that no one actually saw a drop fall until very recently. Despite multiple attempts to catch it in the act, cameras were set up. Observers watched, but the drop always fell just out of view during a recording glitch or between schedule checks. It was almost as if the pitch was shy. In fact, the most famous missed drop occurred in the year 2000 when a webcam had been installed to monitor the experiment. A drop fell, and the camera had broken just hours before. Finally, in 2013, technology and patience aligned. For the first time, a drop was recorded as it separated from the funnel and landed. It wasn't flashy. It didn't splash or bounce. It simply hung there as if unsure about its life choices. And then, plop, it fell. Scientists and science lovers around the world celebrated quietly. Of course, this was a slow-motion victory. So, what exactly does this experiment tell us? At first glance, it might not seem like it tells us much. It's slow, awkward, and mostly uneventful. But in truth, it demonstrates an important concept in physics. Viscosity, that's the measure of a fluid's resistance to flow. Water has low viscosity. It flows easily. Honey is thicker. Masses is thicker still. But pitch has a viscosity about 200 billion times that of water. That's like comparing a racing cheetah to a particularly lazy glacier. The pitch drop experiment also challenges our assumptions about the states of matter. We tend to think of substances as neatly fitting into one of three categories: solid, liquid, or gas. But pitch occupies a strange middle ground. It shatters if struck with a hammer. Very solid, but left undisturbed, it flows like a liquid. It doesn't transition rapidly between states. It simply exists in this glacial ooze of its own design. And while the experiment may seem quaint now, it was genuinely important in demonstrating that not everything that looks solid truly is. Our senses can deceive us. Something might feel hard and unmoving, but under the right conditions and with enough time, it reveals its true nature. Now, here's a delightful twist. The University of Queensland's pitch drop experiment is not the only one of its kind. In fact, there's a similar experiment at Trinity College in Dublin, Ireland. The Irish version began in the 1940s and has its own pitch sample slowly dripping away in a bell jar in the physics department. The Dublin pitch experiment is less well known, but it has one distinct advantage. It's been more successfully observed. The team at Trinity managed to catch a drop falling on video back in 2015, making it a rare instance where the Irish beat the Australians at something involving slow drips and determination. So why keep this experiment running? Well, in a world obsessed with instant gratification, the pitch drop experiment is a quiet act of rebellion. It's a testament to the value of patience, persistence, and curiosity. It reminds us that not all discoveries come with fireworks. Some come with a gentle plop every dozen years or so, and that's still beautiful. There's also something poetic about the fact that the man who started it, Professor Parnell, never lived to see even the third drop fall. He passed away in 1948. Yet the experiment he began continues, still teaching, still mesmerizing people with its slow, sticky elegance. And speaking of sticky elegance, you might be wondering whether the pitch could stop flowing altogether. In theory, yes, if the temperature dropped significantly or the apparatus became compromised. But under current conditions, there's no reason it shouldn't continue. And at its current rate, It might keep dripping for another century or more. Imagine that. A science experiment quietly continuing long after the people who built it, watched it, or even remembered it are gone. A tiny glass funnel filled with ancient tar, keeping time not in seconds or minutes, but in decades and lifetimes. The pitch drop experiment is in some sense a kind of scientific Zen garden. It's not about results in the traditional sense. It's about observation, waiting, trusting that even the slowest processes have something to teach us, if only we're willing to slow down enough to listen. So the next time you feel like everything's moving too fast, emails piling up, news feeds scrolling endlessly, clocks ticking louder than usual, remember the pitch. Sitting in a quiet glass dome in a university lab, doing absolutely nothing dramatic for years on end, and still managing to capture the hearts and minds of curious people around the world. And if that isn't worthy of a bedtime story, I don't know what is. Imagine designing a clock that will still be ticking long after every city you know has crumbled to dust long after your great-great-grandchildren's great-grandchildren have forgotten your name. A clock so patient, so methodically deliberate that it ticks once per year. It chimes once every 100 years. And if you happen to be around in 10,000 years, it will give you a very special cuckoo. This is not a science fiction fantasy. This is the real, currently under construction, quietly ticking marvel known as the clock of the long now. Let's take a deep breath and wind back the gears. The idea for the clock began not with an engineer or physicist, but with a computer scientist and inventor named Danny Hillies. In the late 1980s, Hillies found himself growing concerned with the increasing short-term focus of modern society. Politics, media, business, even science in some cases, seemed increasingly obsessed with what was happening in the next 24 hours or the next quarterly earnings report. Long-term thinking, the kind that spans generations, was falling out of fashion. So he had an idea. What if we built a monument to time itself? A clock that could inspire people to think in terms of centuries and millennia, not just minutes and seconds. A clock that would last 10 0 years, not metaphorically, not poetically, but actually last 10 0 years. In true inventor fashion, Hillies started working on prototypes. He even stored some early versions in a closet at the Massachusetts Institute of Technology. But the idea grew, it resonated, and by the mid-1990s, he had founded the Long Now Foundation, an organization devoted to encouraging long-term thinking and responsibility. The name itself, Long Now, was coined by musician and artist Brian Eno, who joined the project early on. Eno, ever poetic, said that now should be a bigger concept, not this tiny sliver of time we live in, but a long now stretching backward and forward in deep time. The clock they envisioned would not just be a clever piece of engineering. It would be a symbol, a mechanical poem, a reminder that we are part of something vast and unfolding. Now the engineering of such a clock presents a few challenges. Imagine designing something that has to function accurately for 0 years. Batteries won't cut it, computers crash, software becomes obsolete, materials decay. So, how do you make a clock that survives millennia? You start by building it out of incredibly durable materials. The Long Now is being constructed from marine-grade stainless steel, high molybdenum alloys, and ceramic. These materials are chosen to resist corrosion, weathering, and time's usual mischief. There are no plastic gears, nothing that requires oiling or constant maintenance. You also design it to be powered by natural forces. Visitors who climb the installation will help wind it, using human energy to raise weights that power the mechanism. Solar synchronizers will ensure it remains accurate over the centuries, using the position of the sun to correct any drift. The clock is mechanical, entirely analog. It's filled with slow-moving cams, gears, and rods that drive its hands and chimes. One of its more delightful features is the chime generator designed by Brian Eno, which plays a unique melody every day. There are 365 different melodies per year, and no melody will repeat for 10 zeros, 0 years. Let that sink in. No repetition for 10 millennia. The music of time composed slowly and uniquely day after day, and the clock's display. Rather than show you the current hour and minute, the long now clock shows the year, just the year, because when you're thinking in millennia, minutes don't really matter. It's designed to make you feel small in a good way. Now, where is this marvel located? The first full-scale version is being built deep inside a mountain in West Texas, specifically on land owned by Amazon founder Jeff Bezos, who has been one of the clock's major supporters and financial backers. It's not a flashy monument placed in a city square, it's hidden. To reach it, you must hike for hours through rugged desert terrain and ascend a spiraling tunnel carved into the mountain itself. The journey is part of the experience. Time, after all, is not always convenient. The mountain location offers natural protection. It's geologically stable, remote, and less vulnerable to weather, war, or urban expansion. Once completed, the clock will sit quietly waiting for visitors who want to listen to time itself. And that's part of the magic. The clock doesn't run continuously. It's powered when people wind it. So if no one visits for a few years, it simply waits. Time passes, gears pause, and then when someone returns, it resumes right where it left off. There's a profound humility in that design. The clock doesn't demand attention. It simply continues quietly, indefinitely. So why build such a thing? Isn't it just an expensive, over-engineered curiosity? Well, yes and no. It is a curiosity, but it's also a message. It's a challenge to how we think. The long now clock forces us to consider the future not as an abstraction, but as a place that actually exists and will be inhabited by people who may care deeply about the choices we make today. It asks us to imagine what kind of legacy we're leaving, not just in cultural terms, but environmental, technological, and ethical ones. When you stand before a machine designed to last 0 years, you can't help but feel a bit more connected to the flow of history. You think about the builders of Stonehenge and the pyramids. You think about the people who first planted trees that still bear fruit today, and you wonder, what are we building that might last? The Long Now Foundation has other projects, too, like the Rosetta Project, which is preserving human languages on microscopic discs, and the Manual for Civilization, a library of books chosen to reboot society if needed. But the clock is their heartbeat, a quiet, slow, enduring tick in a world full of buzzes and beeps. Of course, there's something charmingly paradoxical about a 10,000 year clock. It requires the most advanced thinking to create something that functions with almost no technology. It uses old-school mechanics to promote futuristic awareness. It celebrates simplicity in an age of complexity. And in doing so, it reminds us that sometimes the best way to move forward is to slow down. There's also an existential calm that comes from knowing that such a thing exists. While news cycles churn and emails multiply and trends flare and vanish, this clock is still sitting in a cave in Texas, marking time with the patience of stone. It does not care who is president. It does not worry about viral videos. It simply exists slow and sure, like the turning of the earth or the drift of continents. And that's perhaps the deepest lesson of the long now clock. Not just that we can build for the long term, but that we should. That slowing down, thinking ahead, and taking care in what we build can offer a kind of peace that's rare in our hurried world. So the next time you glance at the clock and sigh about how fast the day has gone, remember there's another clock hidden in a desert mountain that's barely noticed your year at all. It's still ticking patiently, gently, a quiet echo of the future. And you're part of that future, too. If you've ever looked at a tree stump and counted the rings, you've already dipped a toe into one of the most quietly astonishing scientific fields in existence. It's called dendrochronology, which is a wonderfully fancy word for the study of tree rings, and it's one of the longest-running, most patient sciences humanity has ever cultivated. Pun entirely intended. Now, trees in their dignified swaying silence are not just lovely to look at or excellent for hammocks. They are recordkeepers, timekeepers, actually. Every year, a tree grows a little bit more, laying down a fresh ring in its trunk. Like an organic time-lapse photograph, those rings store clues about what was happening in the environment when they formed. If the tree had a good year, plenty of sunshine, rain, and no stress, it adds a nice wide ring. If it had a rough time, drought, frost, fire, or disease, the ring might be narrow, misshapen, or even discolored. By carefully studying these rings, scientists can reconstruct environmental conditions stretching back thousands of years. Not just how old the tree was, but how wet it was in the year 863, or how volcanic ash in the air affected growth in the year 1380. And unlike other forms of environmental data, tree rings don't require fancy satellite technology or delicate laboratory work. All you need is a core sample from a tree, a microscope, and a lot of patience. Scientists use an instrument called an increment borer, which sounds much more dramatic than it is. It's basically a long, thin tube that extracts a pencilized core from a tree without harming it. That core is then examined under magnification, and each ring is counted and measured. It's a meticulous job, often involving hours spent peering at wiggly lines that look remarkably like a zebra stripe pattern. But here's the magical part. Dendrochronologists can match up tree ring patterns from different trees in the same region. For example, a living tree might be 300 years old. A nearby dead tree, now a timber beam in an old barn, might go back even further. If their ring patterns overlap, scientists can align them like puzzle pieces, extending the record backward in time. Keep doing this tree by tree, and you can create an unbroken chain of data that stretches back thousands of years. In some parts of the world, these continuous ring chronologies go back over 11 zero years. That's longer than written language, longer than agriculture in many places, longer than cities. Through tree rings, we can read the story of climates long before human beings ever thought to write down the weather. Take the bristle-cone pine, for instance. These Gean-led ancient trees live in high-altitude dry regions of the American Southwest. Some are nearly 5,000 years old and still alive. Their twisted trunks and slow growth make them ideal for dendrochronology. In fact, one famous bristle-cone pine, affectionately known as Methuselah, is considered one of the oldest known non-clonal organisms in the world, estimated to be over 800 years old. Imagine that. A tree that began growing while the Egyptian pyramids were just an ambitious twinkle in some architect's eye. Still standing, still growing, still quietly logging each passing year into its wooden memory. But tree rings do more than just measure time. They also help us understand past climate. By analyzing ring widths, wood density, and even the isotopes present in the wood, scientists can infer temperature patterns, rainfall levels, and even solar activity. That means tree rings are vital to climate science. They act as natural proxies, stand-ins that help us fill gaps in historical climate records. For instance, tree ring data has been essential in understanding the so-called Little Ice Age, a period of cooler temperatures that lasted from roughly the 14th to the 19th centuries. By studying trees from this period, researchers could see evidence of shorter growing seasons, increased stress, and lower average temperatures. And the precision is astonishing. Unlike ice cores or sediment layers, which can be a little fuzzy in their annual resolution, tree rings are exact. 1 ring equals 1 year, no guesswork required. Tree rings have also helped us date historical events. A volcanic eruption that blankets a region in ash can leave a telltale mark on tree growth. Trees might produce a narrow ring, or in some cases no ring at all that year. One famous example is the eruption of Mount Mazama in what is now Oregon, which formed Crater Lake around 700 years ago. Trees buried in the resulting atoll have been carbon dated and matched with tree ring chronologies, helping scientists pinpoint the eruption's exact timing with remarkable accuracy. Dendrochronology has even solved archaeological mysteries. Wooden beams from ancient structures can be dated with incredible precision, allowing historians to establish construction timelines. In the southwestern United States, for example, wooden roofs and supports in ancient Peeblin cliff dwellings have been dated using tree rings, giving us a clearer picture of when and how these communities built their homes. But like many good things in science, dendrochronology also requires extraordinary patience. Growing trees takes time, and growing old trees takes a lot of time. That means long-term studies require generational thinking. A researcher might start a chronology in their 20s and spend their whole career slowly adding to it. Some will pass on their data to students who will continue the work. It's science at a glacial pace, but with far more bark. There's also something delightfully humble about it. In an age of space telescopes and particle accelerators, here's a field where progress comes from walking into a forest with a backpack, carefully drilling into a tree, and then carrying a tiny sliver of wood back to the lab. No explosions, no quantum entanglement, just trees and time. One branch of dendrochronology, yes, pun still intended, is dendroclimatology, which focuses specifically on using tree rings to study climate changes. This field has gained urgency as our planet faces rapid environmental shifts. Long-term tree ring data allows scientists to compare current warming trends with natural variations over thousands of years. And the verdict is sobering. The warming we're seeing now is far faster than anything captured in the tree ring record, which means that while trees are slow and steady, the changes we're experiencing now are anything but. Still, there's something comforting in knowing that trees remember. Long after we're gone, the forest will go on keeping time, telling stories through their trunks. With each new ring, a new chapter is quietly added to the great book of Earth's history. And while the modern world spins faster and faster, these trees, some of which began growing before the alphabet existed, are still patiently recording. Not with ink or pixels, but with wood fibers, sunlight, and rain. A story written in silence, but legible to those who know how to look. So, the next time you walk through a forest or see a tree stump after a storm, take a moment to count the rings. Not just to see how old the tree was, but to marvel at what it witnessed. It may have seen plagues and wars, peace and prosperity, droughts and floods, and it remembered it all year by year in circles of growth so thin and precise that they make our digital records look positively clumsy. In the end, tree rings are not just data, they're memories, slow, steady memories etched into the living wood of the world. And like all the best stories, they reward those who listen carefully. When we talk about long experiments, we often mean something that lasts for years, maybe decades. But some experiments stretch their duration into the realm of the unimaginable, not because scientists are overly patient, but because nature itself runs on a schedule that makes our lifespans look like fleeting sparks. Welcome to the world of radioactive decay, where change unfolds over millions, even billions of years, and where atoms quietly transform in slow-motion fireworks that light up our understanding of deep time. At the heart of this story is the humble atom. For most of human history, atoms were thought to be the smallest, most indivisible units of matter, tiny, eternal building blocks that made up everything we see and touch. But in the early 20th century, scientists discovered something remarkable. Some atoms are unstable. They don't want to stay the way they are. Given enough time, they break down into other elements, releasing energy in the process. This is radioactive decay, and it's not just a fascinating quirk of nature. It's one of the most powerful tools we have for measuring the age of the universe. Now, radioactive decay happens at different rates depending on the element in question. Some isotopes, like carbon-14, decay relatively quickly. They're useful for dating things that are thousands, not billions of years old, like archaeological finds or ancient cave paintings. But other isotopes are incredibly patient. Take uranium-238, for example. It has a half-life of about 4.1/2 billion years. That means if you start with a pile of uranium-238, half of it will have decayed into lead-206 after 4.1/2 billion years. The rest will still be uranium just hanging out. This sort of glacial transformation is useful to scientists in a surprisingly practical way. Because we understand the precise rate at which radioactive decay occurs, we can use it like a clock, a very slow, very dependable clock. This method is called radiatric dating, and it allows geologists to determine the age of rocks, minerals, and even entire planets. Let's say a layer of a flow cools and hardens. The moment it solidifies, its radioactive clock starts ticking. Over the eons, the radioactive elements inside it begin to decay at known rates. By comparing the ratio of parent isotopes like uranium to their decay products like lead, scientists can calculate how much time has passed since that rock became solid. And the margin of error surprisingly small. We're talking plus or minus a few million years, which may sound like a lot until you remember we're measuring something that happened 3 billion years ago. This is how we know the Earth is about 4.1/2 billion years old. It's not a wild guess or poetic exaggeration. It's chemistry. We've measured rocks from the Earth, from the Moon, and even from meteorites that fell from space, and they all tell the same story. Our planet and our solar system formed a little more than 4.5 billion years ago. Give or take a few 100 million candles on the birthday cake. But radioactive decay isn't just a dating tool. It's also a natural power source inside the Earth. The heat that drives plate tectonics and volcanic activity is partly sustained by the radioactive decay of elements like uranium, thorium, and potassium. These elements are buried deep in the mantle and crust, slowly releasing energy as they break down, keeping the core hot and the surface geologically active. Without this internal heat engine, Earth might be a cold, lifeless rock drifting through space. So, in a very real way, radioactive decay has helped keep the planet alive. Speaking of natural processes, one of the most astonishing discoveries in this area came in the 1970s in a uranium mine in Oklo, Gabon in West Africa. While analyzing uranium ore, scientists discovered that a specific kind of uranium, uranium-2, 135, was less abundant than expected. This was puzzling because uranium-2, 135, is the isotope used in nuclear reactors, and it's normally found in consistent proportions. So what was going on? It turned out that about 2 billion years ago, a very special combination of conditions had occurred in the Olo region. Groundwater seeped into uranium-rich rock, creating the perfect setup for a natural nuclear reactor. For hundreds of thousands of years, fission reactions took place underground, completely naturally, generating heat and altering the surrounding rock. In essence, nature had built a nuclear reactor long before humans ever dreamed of splitting the atom. This natural reactor operated in cycles with water, acting as a moderator to keep the reactions going. When the water boiled off, the reaction would slow down, only to start up again once the area cooled and groundwater returned. Scientists estimate that these natural reactors operated intermittently for up to 1 million years. That's longer than Homo sapiens have existed. The Olo discovery was a revelation. It proved that under the right conditions, nuclear fission could occur naturally. And it gave scientists invaluable insights into how radioactive waste might behave over geological time scales. In fact, studies of Oklo have helped shape the strategies for storing nuclear waste, offering a glimpse into what might happen over hundreds of thousands or even millions of years. But radioactive decay doesn't stop with the Earth. It reaches out into space and across the vast canvas of the cosmos. Some of the elements created in supernova, the violent deaths of massive stars, are radioactive. Their slow decay gives off light and heat, which we can observe from millions of light years away. In a way, radioactive decay is part of how the universe remembers its own history. One of the most poetic uses of radioactive decay is in understanding the age of stars. Scientists can measure the abundance of radioactive isotopes like thorium and uranium in ancient stars, and use their known decay rates to estimate how long those stars have been burning. It's cosmic clockwork, ticking quietly in the heart of distant suns. Of course, radioactive decay is also the foundation of nuclear power and nuclear weapons. It's a double-edged sword capable of powering cities or leveling them. And that's why it's so crucial to understand not just the physics, but the long, slow implications. Waste from nuclear reactors, for instance, remains dangerous for tens of thousands of years. That means we need to think long-term, very long-term, about where and how we store it. Some countries are building deep geological repositories, carving secure vaults into stable rock formations that haven't moved in millions of years, hoping they'll remain undisturbed for tens of thousands more. These efforts highlight a recurring theme in the story of radioactive decay: the need for patience. Whether we're dating rocks, powering homes, or pondering the legacy of our technologies, the lesson is clear. Time doesn't care about our schedules. Atoms move to their own rhythm, and that rhythm is often slower than we can easily comprehend. And perhaps that's what makes radioactive decay such a compelling example of long-term science. It reminds us that not all experiments need laboratories. Some are happening all around us all the time in the quiet hum of the earth and the faint glow of distant stars. They unfold in spans so long that they challenge our imaginations. Yet, with the right tools and a little patience, we can listen in. So the next time you hear someone say, "Time flies," just remember that somewhere deep underground, an atom of uranium is taking a very slow breath, preparing for a transformation that won't be complete for another few billion years. And all the while, scientists are watching, waiting, listening to the soft, steady rhythm of the universe unraveling itself, one atom at a time. In the heart of Antarctica and Greenland, thousands of feet below the ice-covered surface, lie bubbles. Tiny ancient bubbles trapped in frozen time. They are pockets of air, real breathable air from thousands, even hundreds of thousands of years ago. If you could somehow pop one open and take a deep breath, you'd be inhaling the atmosphere your distant ancestors once breathed. It would smell no different, but chemically it would whisper stories of past climates, long forgotten volcanic eruptions, and ancient skies heavy with dust. Welcome to the world of ice cores, one of the most elegant time machine science has ever built. In this frozen archive, scientists have found a way to read the Earth's history, not from books or fossils, but from the silent icy layers laid down year after year, snowfall after snowfall for over 800 years. Ice core science is all about layers. Much like tree rings, each year of snowfall creates a new stratum of ice. Over time, as snow piles on top of snow, the lower layers are compressed into solid ice. This ice isn't just frozen water. It's a layered document storing everything from atmospheric gas concentrations to ash particles, sea salt, pollen, and even microbes. Each layer captures the state of the planet at the time it formed, offering a remarkably detailed timeline of Earth's environmental history. The process of retrieving an ice core begins with drilling. Picture a long cylindrical drill bit spinning its way deep into the polar ice sheets, extracting slender columns of ice, sometimes stretching more than 2 m below the surface. These cores are carefully removed, packaged like precious artifacts, and flown to laboratories where they are stored at sub-zero temperatures to keep them as pristine as possible. One of the most famous drilling sites is the Epicodome C project in Antarctica, where scientists extracted an ice core that extends back more than 800 years. That means we have a year-by-year snapshot of Earth's climate stretching almost 1,000,000 years into the past. Another site, the Greenland project, has similarly provided valuable records of the Northern Hemisphere's climate history. So, what do scientists do with these frozen time sticks? They analyze the bubbles. Trapped within each layer are tiny pockets of ancient air. And by studying their composition, researchers can reconstruct the concentrations of greenhouse gases like carbon dioxide and methane. These records show us with stunning clarity how the Earth's climate has fluctuated naturally over time. Ice core data has revealed the cyclical nature of ice ages, periods of warming, and dramatic shifts that happened in a matter of decades. For instance, the transition out of the last ice age around 20,000 years ago wasn't a slow and steady thaw. In some places, temperatures rose by more than 10 degrees in less than a century. That's a blink of an eye. Geologically speaking, ice cores help scientists see these rapid changes and understand what might have caused them. Shifts in ocean currents, changes in Earth's orbit, or massive releases of methane from melting permafrost. And because we can compare these natural patterns to modern measurements, we can also see what's unprecedented. In recent decades, carbon dioxide levels have skyrocketed far beyond anything seen in the last 800 years. The bubbles don't lie. They tell us that while Earth's climate has always changed, it has never changed this fast or this dramatically in such a short span of time. Not without help from human activity, but ice scores aren't just climate detectives. They're also time capsules of major global events. Volcanic eruptions, for example, leave distinct chemical fingerprints in the ice. Sulfate spikes in a certain layer can be linked to known eruptions like the massive explosion of Mount Tambora in 1815, which caused the year without a summer. Crops failed, temperatures dropped, and poets like Mary Shelley wrote gloomy novels by candlelight. All of that drama captured in a thin layer of ice. Even more ancient eruptions, ones that humans didn't witness, are recorded in the ice. Scientists can use these signals to reconstruct a timeline of volcanic activity stretching back hundreds of thousands of years. These records help us understand how eruptions have influenced global temperatures, agriculture, and even human migration patterns. There are even layers that contain microscopic sea salt, blown in from distant ocean changes in wind patterns. Pollen grains tell us about shifting vegetation. Traces of cosmic dust hint at meteor impacts. It's like a high-resolution documentary of the planet's behavior shot entirely in shades of white. And here's a delightful twist. Ice core scientists often work in pristine, isolated environments for weeks or months at a time. Their field labs are usually remote, freezing, and completely cut off from modern distractions. It's a kind of monastic existence. Just you, the drill, the cold, and the slowly unfolding narrative of deep time. The actual drilling is slow and methodical, requiring careful calibration and endless patience. And once a core arrives back at the lab, the analysis can take years. These are not quick experiments, but the reward is a front-row seat to the memory of the planet. Some scientists even get poetic about it. They describe the ice as whispering or singing or holding its breath. And when you consider that these frozen layers have waited quietly for hundreds of thousands of years just to be read by a curious mind in a lab coat, it's not hard to see why. Interestingly, ice cores aren't limited to the poles. Scientists have also extracted cores from tropical glaciers, such as those in the Andes and the Himalayas. These ice records are often more fragile and more endangered thanks to rapid warming. But they offer valuable data about regions that are otherwise hard to study. Some tropical cores have revealed that massive droughts helped bring down ancient civilizations like the Mayans. That's the beauty of ice. It can show us how climate shapes human history. As the climate warms, though, we face a sobering reality. Some of these frozen records are melting. Glaciers that took tens of thousands of years to form are disappearing in decades. That means scientists are racing against time to preserve these ice cores. Efforts like the Ice Memory Project aim to store backup cores in protected vaults, essentially creating cryogenic libraries for future generations. Think of it as insurance for planetary memory. And while most of us may never visit a glacier or hold an ice core in our hands, the impact of this research reaches all of us. Thanks to these frozen archives, we have a clearer understanding of how Earth's systems work. We can see the fingerprints of ancient disasters and patterns of recovery. We can tell the difference between natural cycles and human-caused changes. And perhaps most importantly, we can imagine what lies ahead. It's a reminder that the Earth has been through tremendous changes before, coolings, warmings, upheavals, and has always found a way to adapt. The question, of course, is whether we can adapt with it. So the next time you see snow falling or ice forming on your window, take a moment to appreciate just how much knowledge can be hidden in something so ordinary. Those tiny crystals, those frozen droplets, they're part of a much larger story, one told slowly, quietly, and with infinite patience. In a world that so often rewards speed and noise, ice cores invite us to pause, to listen, to respect the quiet memory of the world beneath our feet. Because sometimes the coldest places hold the warmest truths. Let's talk about DNA, that miraculous, twisty little molecule inside almost every cell of your body. The one shaped like a spiral staircase if it were designed by a minimalist architect with a flair for symmetry. DNA is the instruction manual for life, written in a 4-letter code, and it's been humming quietly along for billions of years. But here's something you might not know. DNA is also one of the slowest and most fascinating clocks in science. This clock is known as the molecular clock. Unlike a ticking wall clock or a grandfather clock that chimes dramatically every hour, the molecular clock keeps time through mutations. Those tiny random changes in DNA that happen when cells copy themselves. Most of these mutations are harmless. Some do nothing at all. Others tweak traits ever so slightly. But over long periods of time, millions of years, these mutations pile up like snowflakes in a silent storm. And scientists have learned to read this gentle snowfall of genetic change like timestamps in the grand story of evolution. The concept of the molecular clock was first proposed in the early 1960s by biologists Emil Zucker and Linus Pauling. Yes, that Linus Pauling, the Nobel Prize-winning chemist who also campaigned for peace and vitamins. They noticed something remarkable while comparing the proteins of different species. The number of differences between their genetic codes was roughly proportional to the time since they had diverged from a common ancestor. It was as if mutations accumulated at a fairly regular rate, like grains of sand trickling through an evolutionary hourglass. This idea was revolutionary. It suggested that by counting the differences in DNA between two organisms and knowing the average rate at which mutations occur, scientists could estimate how long ago those organisms shared a common ancestor. In other words, DNA could serve as a calendar of life. Of course, like all good scientific ideas, it's a bit more complicated than that. Mutation rates aren't perfectly consistent. They can vary depending on the species, the gene in question, the type of DNA, and even environmental conditions, but with enough calibration using fossil records and known evolutionary events, molecular clock becomes a surprisingly powerful tool. Let's say you're comparing the DNA of humans and chimpanzees. We know from fossil evidence that our last common ancestor lived about 6 to 7 million years ago. By comparing specific genes between the two species, scientists can count how many mutations have occurred in each lineage. If humans have accumulated, say 60 mutations in a particular gene since that split, and chimpanzees have accumulated about the same number, that gives you a mutation rate. And once you have that rate, you can start comparing all kinds of species. This has led to some remarkable discoveries. For example, scientists once debated when whales evolved from land-dwelling ancestors. Fossils gave some clues, but the molecular clock helped to narrow down the timing to roughly 50 million years ago, give or take a few million. That's not bad for something that once required a full skeleton and a lot of luck to piece together. The molecular clock also played a major role in solving the mystery of when modern humans spread across the globe. By comparing the mitochondrial DNA passed down through mothers from people all over the world, researchers estimated that all modern humans trace back to a common maternal ancestor who lived in Africa roughly 150 to 200 years ago. She wasn't the only woman alive at the time, of course, but her lineage is the one that survived unbroken to the present day. Scientists call her mitochondrial Eve, and while she probably didn't know it, she helped shape the entire genetic legacy of our species. Speaking of mitochondria, let's pause to appreciate them. Mitochondria are the power plants of your cells, turning food into usable energy. But they also carry their own tiny loop of DNA, separate from the DNA in your cell nucleus. This mitochondrial DNA mutates at a different, often faster rate, which makes it especially useful for studying more recent evolutionary events, like the spread of populations or the domestication of animals. In fact, molecular clock studies have helped scientists figure out when dogs split off from wolves, when cattle were first domesticated, and how modern crops like corn and wheat were selectively bred from wild ancestors. Imagine tracing the genetic fingerprint of your golden retriever all the way back to some clever wolf that decided to stop biting humans and start eating their leftovers. It's all there in the slow drip of DNA. One of the most exciting recent applications of the molecular clock is in the field of ancient DNA. Thanks to improved techniques in extracting and sequencing old genetic material, researchers have been able to analyze the DNA of Neanderthals, Denisovans, and even long-extinct mammoths. By comparing these ancient sequences to those of modern humans, scientists can trace migration patterns, interbreeding events, and adaptations to changing environments. For example, Neanderthal DNA makes up about 1 to 2% of the genomes of most people of European and Asian descent. That means that tens of thousands of years ago, there was a period of overlap, of mingling, shall we say, between anatomically modern humans and their Neanderthal cousins. The molecular clock helped determine when these interactions likely occurred, giving us a clearer picture of our evolutionary family tree. Now, not every mutation is created equal. Some parts of the genome change faster than others. For instance, non-coding regions, those stretches of DNA that don't directly build proteins, tend to mutate more freely. Protein-coding genes, on the other hand, are under stricter evolutionary pressure, since changes there can be harmful. By focusing on different types of genetic material, scientists can adjust the speed of the clock to suit the time frame they're studying. There's even a molecular clock buried in viruses. In fact, it's been an essential tool for tracking the evolution of viral outbreaks. The CO-19 pandemic gave us a crash course in real-time molecular clockwork as scientists around the world sequenced thousands of viral genomes to track how the virus was mutating, spreading, and adapting. By comparing these sequences and noting the changes, researchers could estimate how long the virus had been circulating and identify emerging variants. In that case, the molecular clock wasn't just an academic curiosity. It was a vital part of the global response. It helped guide public health decisions, vaccine design, and our understanding of viral behavior. All thanks to a principle discovered more than half a century ago in a humble lab built on the slow, steady tick of DNA. Of course, there's something deeply philosophical about the whole concept. Your body is made up of trillions of cells, each one containing DNA that has been copied and passed down through uncountable generations. And every time your DNA was replicated, whether in a bacterium, a fish, a primate, or a human, a few tiny changes occurred. Over billions of years, those little changes accumulated. Some led to new traits, some faded into obscurity, but all of them left a mark. You are, in a very real sense, a walking experiment in molecular timekeeping. Your genome is the sum total of eons of trial and error, of tiny missteps that turned into milestones. And whether or not you ever think about it, your cells are still ticking, still mutating, still participating in the slow, cosmic experiment of life. It's easy to forget that in the rush of everyday living, but the molecular clock is always running, not in the background, but right at the heart of who you are, quiet, steady, and impossibly ancient. So the next time you look in the mirror, consider this. Behind your eyes is a story written in 4 letters, shaped by billions of years, and still unfolding. And somewhere in that story, ticking softly like a heartbeat in the fabric of your being, is the slowest experiment you'll ever take part in. Life itself. Deep beneath the surface of the earth, sealed in ancient crystals, frozen in polar ice and buried in desert salt flats, some of the smallest life forms on the planet have been playing the longest waiting game in biological history. These are microbes, bacteria, spores, and other microscopic beings that have paused their lives for thousands, even millions of years, waiting patiently for just the right moment to spring back into action. If there were an Olympic event for persistence, these organisms would not just win. They'd outlive the referees, the stadium, and possibly the entire sport. Welcome to the world of microbial dormancy, a field where life slows down to an almost imperceptible crawl, where metabolism hibernates, and where the boundary between life and non-life becomes beautifully blurry. It's a realm that challenges our understanding of biology, resilience, and time itself. Let's begin with spores, not the kind you sprinkle on a salad or find puffing from a mushroom in the woods, but bacterial spores. These are special survival forms that some bacteria produce when conditions get tough, when food runs out, water disappears, or temperatures swing to extremes. Rather than die off, these bacteria essentially build themselves a tiny bunker. They shed water, thicken their walls, slow their metabolism to a crawl, and enter a state of suspended animation. Think of it as hitting the pause button on life, but with all the sophistication of a maturized space capsule, and they can stay in that pause state for a very, very long time. In laboratories, scientists have revived spores that were thousands of years old, taken from the digestive tracts of ancient mummies, or sealed in permafrost since the Ice Age. These bacteria, once considered long dead, sprang back to life when given warmth, moisture, and nutrients. It's as if they had simply been napping, a millennial-long nap with no alarm clock in sight. One particularly eyebrow-raising case involved salt crystals from a New Mexico salt mine. Researchers found fluid inclusions, tiny pockets of ancient brine, trapped inside crystals that were dated to be around 250 million years old. That's older than the dinosaurs. That's older than flowering plants. And inside those pockets, they found what appeared to be viable microorganisms. Now, this kind of claim is controversial. It's difficult to conclusively prove that the microbes didn't sneak in through contamination. But even if we take a more conservative view, there's plenty of solid evidence that microbes can survive for hundreds of thousands, possibly millions of years in states of dormancy. Permafrost samples from Siberia have yielded viable bacteria, estimated to be 500,000 years old. Antarctic ice has preserved microbial life from glacial periods, long before human civilization began. What makes this possible it comes down to a few impressive biological tricks. First, these dormant cells repair their DNA slowly over time, even when metabolically inactive. They also produce specialized proteins and sugars that protect their internal structures from damage caused by freezing, drying, or radiation. Some even form a kind of glassy matrix inside their cells to keep everything stable. These mechanisms act like biological bubble wrap, preserving the essential components of life during long cold waits. There's also tardigrades, of course, those famously indestructible water bears. While not microbes themselves, tardigrades are microscopic animals known for their ability to survive extreme environments, from the vacuum of space to boiling water. They do this by entering a state called cryptobiosis, during which they expel nearly all water from their bodies and suspend metabolic activity entirely. In this state, they've been known to survive for decades without food or water. And while decades might sound short compared to bacteria's million-year record, it's still impressive for a creature with tiny feet and a digestive tract. This ability to pause life has major implications for science, particularly in the field of astrobiology. If bacteria can survive millions of years frozen in ice or trapped in salt on Earth, it raises the possibility that life might survive similar conditions on other planets or moons. Europa, one of Jupiter's moons, has a frozen surface with signs of subsurface oceans. Mars, too, has polar ice caps and evidence of past liquid water. Could dormant life be waiting in those alien soils, just as it waited in our ancient deserts? NASA certainly thinks it's possible. Some of the life detection missions to Mars include instruments designed to look for dormant or recently reactivated microbes. If life ever did exist on Mars, it may have taken a page from Earth's microbial playbook, retreating into dormancy as the planet dried out and cooled, waiting patiently for moisture or warmth to return. Back on Earth, scientists are now exploring whether dormancy plays a role in long-term ecosystem survival. Soil, for example, is teeming with microbial life, but not all of it is active. In fact, it's estimated that in many soils, as much as 90% of the microbial population is dormant at any given time. They're essentially on standby, waiting for the right conditions to come back online. This dormant pool of life acts as a kind of microbial seed bank, helping ecosystems recover from disturbances like droughts, fires, or human development. Dormancy also plays a role in health. Some disease-causing bacteria can enter dormant states to avoid antibiotics, which typically target actively dividing cells. This is one reason why some infections can be stubbornly recurrent. The bacteria hide out, wait for the coast to clear, and then re-emerge. Tuberculosis is a classic example. The bacteria responsible can remain latent in the body for years, even decades, before causing symptoms. Understanding how dormancy works at the cellular level could lead to better treatments and new ways of combating persistent infections. And let's not forget the potential applications in biotechnology. Scientists are studying these hardy microbes to develop better ways of preserving vaccines, storing genetic material, and even designing long-term life support systems for space travel. If bacteria can survive for thousands of years in a frozen cave, why not apply those same principles to human medicine, food preservation, or interplanetary exploration? But beyond the science, there's something quietly poetic about microbial dormancy. In a world obsessed with speed and productivity, these tiny organisms remind us that sometimes the best strategy is to wait, not to rush, to slow down so completely that time becomes almost Meaningless, they don't resist change, they simply outlast it. In a way, microbial dormancy is a meditation on resilience. Life doesn't always need to thrive in the traditional sense. Sometimes enduring is enough, waiting quietly, patiently in the dark and the cold until the moment is right. Then, and only then, does life flicker back into motion, like a light turned back on in a forgotten room. You might imagine this happening deep beneath the Antarctic ice. A small bubble of water forms during a seasonal thaw, trickling into a crack in the ice. The temperature rises just enough. A dormant microbe asleep for thousands of years senses the change. Slowly it rehydrates, its membranes soften, enzymes awaken, it begins to divide, one cell becomes two, then four, then a colony. Life resumes as if nothing had happened. No fanfare, no dramatic music, just a quiet continuation of something that never really ended. And in that moment, the line between death and life blurs, not with lightning bolts or miracles, but with a subtle, gradual unfolding, a reminder that life's grip is not always loud or visible. Sometimes it waits, and in waiting it survives. So the next time you hear someone say, "Life finds a way," you can smile knowing that in some forgotten pocket of ice or salt, it already has. It just hasn't said hello yet. In a quiet fire station in Livermore, California, a single light bulb glows softly above the engines. It's not bright, in fact, it's quite dim compared to modern bulbs. Just a gentle amber-colored glow that wouldn't light up much more than a small corner of a room. But this bulb isn't here to impress with its wattage. It has a different kind of brilliance, longevity. This humble light bulb has been on almost continuously since the early 1900s. That's right. A bulb that has been glowing through wars and moon landings, through the invention of television, smartphones, and the internet. It has outlived multiple fire chiefs, witnessed the birth and retirement of countless firefighters, and quietly watched as the world transformed around it. This is the Centennial Light, quite possibly the most enduring bulb in the history of illumination. Installed in either 1901 or 1902, historians are still debating the exact date. The Centennial Light began its life as a standard carbon filament light bulb. It was made by the Shelby Electric Company in Ohio, a company long since gone, and it originally hung in the Livermore Fire Department's hose cart house before being moved several times, always continuing its steady, sleepy glow. Now, just to clear the air, the bulb hasn't been on, literally every second, for over a century. There have been a few interruptions, brief power outages, the occasional move from one building to another, but aside from those tiny blips, it's been shining for well over 1 million hours. For comparison, a modern incandescent light bulb is expected to last about 1,000 hours. That means the Centennial Light has outlived over 1,000 of its more energetic, short-lived cousins. So, how is this even possible? Did the Shelby Electric Company make their bulbs with a secret ingredient? Were the engineers of the early 20th century simply better at building things that lasted? Or is this a case of miraculous electrical luck? The truth, as usual, lies somewhere in the details. First, let's talk about design. The Centennial Light was made during a time when bulbs were engineered for durability rather than brightness. Its filament is made of carbon, not tungsten like most modern bulbs. Carbon filaments don't burn as hot as tungsten, which means less stress on the bulb and a longer life. But they also emit less light, which is why you rarely see them used today. The Centennial Light was only designed to emit about 4W of light, which is not much more than a strong nightlight. It's not going to brighten up a football stadium, but it will persist. Second, there's the matter of voltage. The bulb originally ran at around 120 volts, but over the years, it's been connected to a regulated power supply that gives it a slightly lower steady voltage. This reduces the stress on the filament and prevents surges that might otherwise cause it to fail. In other words, it's not just about the bulb itself. It's about how gently it's been treated. A slow and steady approach, perfectly fitting for an experiment in patience. Another factor is the filament design. Unlike modern coiled filaments that are designed to glow brightly and burn out quickly, early bulbs used simpler, straighter filaments. These weren't as efficient at converting electricity into light, but they were robust and thick. Less light, more longevity. All of this makes the Centennial light something of an accidental experiment. No one expected it to last this long. No one planned a grand endurance test, but through a mix of solid engineering. This clever cross-referencing extends radio, carbon dating back over 14 zero years with impressive precision. And then there's the bomb effect. During the height of nuclear weapons testing in the 1950s and 60s, the amount of carbon-14 in the atmosphere nearly doubled. This sudden spike, known as the bomb pulse, is actually useful today. It allows scientists to precisely date materials from that era, including human tissues, making it a handy tool in forensics and environmental science. There's even a slightly eerie twist. Carbon-14 is now so pervasive that it shows up in modern manufactured materials, including plastics and synthetic fabrics. This means that radiocarbon dating is sometimes used to detect fraud in the art and antiquities market. A medieval painting with a canvas made from 20th century cotton or an ancient wine with synthetic corks busted by the patient little atoms of C14. But perhaps the most fascinating aspect of radiocarbon dating is what it tells us about ourselves, not just our history, but our place in the natural world. Because carbon-14 is not some external force, it's part of you. Right now, inside your bones, muscles, and breath, there are atoms of C14 gently ticking away, the result of cosmic rays striking the upper atmosphere. You are in a very literal sense part of this vast, slow experiment. You're made of stardust and also of time. And someday, when your body becomes part of the soil or is buried in sediment, those atoms will keep ticking, waiting, measuring, quietly becoming a future day, to point in someone else's timeline. There's a calm kind of poetry in that. The idea that even in death, something of us remains measurable, not in the emotional or spiritual sense, but in the most grounded atomic way. You can't stop it. You can't speed it up. It just is. So the next time you see a museum plaque with a date like circa 200 years before present, know that it wasn't just guessed or estimated. It was calculated with exquisite care based on the decay of carbon atoms that once danced in sunlight, passed through leaves, and helped shape a life long since gone. In many ways, radiocarbon dating is a lesson in patience. It's a method that waits. It doesn't rush to conclusions. It lets the atoms do the talking slowly, surely, one half-life at a time. And while it may seem quiet and unassuming, this method has rewritten history books, illuminated forgotten cultures, and deepened our understanding of the planet we call home. All from a single isotope drifting gently through time. Imagine trying to solve a mystery where the clues are scattered across millions of years, hidden inside the very shape of life itself. No fingerprints, no witnesses, just bones, teeth, and the occasional strand of ancient DNA. Welcome to the science of human evolution, where the experiment isn't performed in a lab, but played out slowly, painstakingly through time. And the longest-running experiment of all, United States, the human species, a living, breathing case study in what happens when a clever primate starts walking upright, using tools and telling stories. We are both the subject and the observer in an ongoing evolutionary journey that's taken hundreds of thousands of years so far, and it's still going. The idea that humans evolved over time was once considered radical. But today, thanks to a century and a half of fossil discoveries, genetic analysis, and comparative anatomy, it's one of the most thoroughly supported ideas in science. And while the full story of our evolution is still being written, we now have a pretty solid understanding of how we got here and where the clues continue to lead us. Let's start with a brief stroll through deep time. Our story begins roughly 7 million years ago in Africa, with the earliest known hominins creatures that were more closely related to humans than to chimpanzees. One of the earliest contenders is Sahelanthropus chadensis, a fossil skull found in Chad that shows a mix of ape and human-like features. It had a small brain about the size of a modern chimp's, but its flat face and position of the foramen magnum, the hole where the spine connects, suggests it may have walked upright. That's a theme we'll see again and again. Bipedalism, the shift from walking on all fours to walking on two legs. It's one of the defining traits of our lineage. While it might seem like a trivial change, it had profound implications. Walking upright freed up the hands to carry tools, infants, and food. It also allowed our ancestors to see over tall grasses and to cover large distances more efficiently in the shifting African savanna. Over the next few million years, several species of early humans appeared and disappeared. There was Australopithecus afarensis, best known through the fossil named Lucy, discovered in Ethiopia in 1974. She lived about 2 million years ago and had a small brain and long arms for climbing, but her pelvis and leg bones clearly show she walked upright. Lucy's kind may have used simple tools, though nothing sophisticated enough to leave behind a strong archaeological footprint. Eventually, around 5 million years ago, a new genus emerged, Homo. These were our more direct ancestors. Homo habilis is often called the handyman because of its association with the first clear evidence of stone tools, sharp-edge flakes used to cut meat, crack bones, and scrape hides. Tool used likely played a major role in shaping the evolution of the human brain. With tools came more efficient food gathering, which may have enabled the growth of bigger, more complex brains. From there, the evolutionary path leads to Homo erectus, a remarkably successful and long-lived species. Emerging nearly 2 million years ago, Homo erectus spread out of Africa and into Asia and Europe. This was a true globe-trotter, walking upright, using fire, and crafting increasingly sophisticated tools. Some evidence suggests Homo erectus may have even constructed simple shelters and cooked food. Impressive milestones for a species whose brain was still smaller than ours. Meanwhile, back in Africa, evolution continued. Homo heidelbergensis, a later species, may have given rise to both Neanderthals in Europe and Homo sapiens in Africa. The Neanderthals, contrary to outdated stereotypes, were not brutish cave dwellers, but intelligent, skilled humans who made tools, cared for their sick, and likely had language and culture. Their skulls were robust, their bodies built for cold climates, and their brains actually slightly larger than ours. And then around 300 years ago, something remarkable happened. Homo sapiens, modern humans, emerged. Our species with rounded skulls, small faces and high foreheads, and with something else too, symbolic thought. That's the turning point that sets us apart. We began making art, burying our dead with care, crafting jewelry, and eventually developing language, agriculture, cities, and space probes. But the story didn't stop there. One of the most extraordinary things about human evolution is how much we've learned by looking not just at bones, but at genes. The field of paleogenetics, recovering and studying ancient DNA, has added a whole new dimension to the timeline. In 2010, scientists successfully sequenced the Neanderthal genome and made a surprising discovery. Most people of European and Asian descent carry around 1 to 2% Neanderthal DNA. That means our ancestors didn't just replace Neanderthals. They interbred with them. Neanderthals aren't a separate branch that ended. They are part of our extended family tree. Even more unexpectedly, another group called the Denisovans entered the picture. Identified from just a finger bone and a few teeth found in a Siberian cave, Denisovan turned out to be a distinct population that also interbred with modern humans. Today, people from parts of Southeast Asia and Oceania carry Denisovan DNA, including genes that help with things like oxygen use at high altitudes. These genetic breadcrumbs reveal a messy interwoven history. Rather than a simple linear march from ape to human, our evolution was more like a braided stream. Different human populations branching, mixing, diverging, and occasionally reuniting. It's a slow experiment, but a grand one. An experiment in adaptation, cooperation, and survival. Over millions of years, humans have responded to ice ages, droughts, volcanic eruptions, and shifting ecosystems. We've adapted our diets, our technologies, and even our physiology. Take skin color, for example. Human skin color evolved in response to levels of ultraviolet radiation. Darker skin provides protection in high UV environments, while lighter skin allows for more vitamin D production in low UV areas. It's a beautiful biological response to geography, and one that tells a story about where our ancestors lived and thrived. And it's not over. Evolution doesn't have a pause button. Modern humans are still evolving, though not always in obvious ways. Genes associated with lactose tolerance, our ability to digest milk into adulthood, have spread in populations that historically raised dairy animals. Certain genetic traits related to disease resistance or altitude adaptation are still under selection today. Even in the age of antibiotics and air travel, natural selection is quietly shaping our future. Cultural evolution has also accelerated. Language, writing, agriculture, and digital technology have reshaped how we live, think, and interact. Unlike genetic evolution, which happens slowly over generations, cultural evolution can transform society within a single lifetime. It's part of the same story, though. Our story is a species that adapts, invents, and remembers, and now we're at a curious crossroads. For the first time in history, we have the power to influence our own evolution directly. Through gene editing, biotechnology, and artificial intelligence, we're tinkering with the very mechanisms that shaped us. The question is no longer just where did we come from, but also where do we go from here? Should we enhance our bodies and minds? Should we attempt to eliminate certain diseases at the genetic level? Should we send humans to live on other planets and watch as isolated populations once again evolve independently, perhaps becoming something new? These are the kinds of questions that the longest experiment in science invites us to ask, not just about our past, but about our future. And perhaps the most profound realization is this: we are not the end of the story. We are a snapshot, a single frame in a long, unfolding film. There were humans before us who were different, and there may be humans after us who are just as different from us as we are from Neanderthals. That's not a failure. That's the beauty of evolution. It's not about perfection. It's about change. Constant, subtle, relentless change. So the next time you look in the mirror, consider this: your face, your hands, your heartbeat. They are the product of millions of years of trial and error, survival and adaptation. You are the descendant of creatures who outlasted droughts, dodged predators, raised children, and crossed continents. You are living evidence of an experiment that's still unfolding, and it's one we're all part of every single day. Tucked away in a laboratory in Germany, in a small sealed flask of clear liquid, something very strange has happened. Or perhaps more accurately, not happening. The liquid is pitch, a tar-like substance made from the distillation of wood or coal, and it's been sitting there very patiently for decades. To the naked eye, it seems frozen in time, perfectly still, utterly motionless. But if you wait long enough, really long enough, you'll witness a drop form, stretch, and slowly fall. And by slow, we don't mean a few minutes or hours. We mean years, nearly a decade between each drop. Welcome to one of the slowest and most oddly mesmerizing experiments in history, the pitch drop experiment. A test so leisurely that it's easy to forget it's even happening at all. There are actually a few versions of this experiment around the world, but the most famous one began in 1927 at the University of Queensland in Brisbane, Australia. A physicist named Professor Thomas Parnell wanted to demonstrate to his students that some materials which seem solid at room temperature are in fact very slow-moving fluids. Pitch, also known as bitumen, appears solid. You can hit it with a hammer and it shatters like glass. But it's technically a fluid. It just flows so slowly that it requires years to notice any movement. To make his point, Parnell heated some pitch until it became pourable, then poured it into a glass funnel. After letting it settle for a few years, it was a different era. He cut the neck of the funnel in 1930, allowing the pitch to begin dripping, and then he waited. Over the years, the pitch has formed thick, glossy drops that slowly, agonizingly grow and stretch until they finally fall into a waiting beaker below. The first drop took 8 years, the second another 9. As of today, only 9 drops have fallen, with the 10th expected sometime soon. But no one knows exactly when. It could be next year or the one after that. The experiment is in no hurry. In fact, no one has ever actually seen a drop fall in real time. It's the ultimate test of patience and humility. In 1979, a camera was set up to record the drop, just in case it happened after hours. But there was a malfunction. The next attempt came in 1988 with another camera. That time, the drop fell during a 20-minute moment when the camera had been turned off for maintenance. In 2000, another drop fell once again unobserved. Nature, it seems, enjoys a little dramatic irony. But finally, in 2014, a camera at Trinity College, Dublin, captured the moment a drop separated from the pitch above. It was caused for celebration in the very niche world of ultra-slow fluid dynamics. The footage shows a thick black glob slowly stretching downward, clinging to the funnel above as it narrows into a neck, then suddenly letting go. After nearly a decade of build-up, the drop lands with no splash, no sound, just a slow exhale of progress. So, what exactly is going on inside that funnel? Why does pitch behave this way? It comes down to the nature of viscosity. Viscosity is a measure of a fluid's resistance to flow. Water has low viscosity, it moves easily, honey is thicker. Molasses is thicker still. Pitch is around 200 billion times more viscous than water. That's why it doesn't move in any way that's visible to the human eye. But technically, it's still flowing. The molecules within it are slowly rearranging, creeping downward under the influence of gravity. This experiment isn't just a fun curiosity. It's a fascinating demonstration of non-Newtonian fluids, substances that don't behave in the straightforward way we expect from liquids. Pitch seems solid, but it isn't. It blurs the line between phases of matter, challenging our everyday understanding of solids and liquids. And there's something almost poetic about that. We often think of scientific discovery as dramatic. Eureka moments, flashing lights, explosions in the lab. But the pitch drop experiment is the complete opposite. It's science at its most restrained, most deliberate, most patient. It's a lesson in what happens when you trust the process, even when the process unfolds at a glacial pace. It's also a reminder of the importance of keeping old experiments going. Thomas Parnell died in 1948, long before the third drop had fallen. But the experiment continues, maintained by successive generations of scientists. It's a living legacy handed down like a family heirloom. You don't get immediate gratification from it, you get continuity. And in a world that's increasingly obsessed with speed, there's something deeply comforting about a scientific inquiry that takes nearly a century to unfold. That continuity has made the pitch drop experiment something of a scientific celebrity. It's in the Guinness Book of World Records as the world's longest continuously running laboratory experiment. It has fans who check the webcam updates, scientists who calculate the viscosity of pitch using mathematical models, and even occasional debates over whether a drop counts if it touches the one before it without fully separating. Yes, the pace is slow, but the passion is real. There's another, perhaps even more fascinating pitch drop experiment underway at Trinity College, Dublin. This version was started in 1944 by Professor Ernest Walton, a Nobel laureate in physics. And unlike the Queensland version, it was set up to sit entirely untouched. No beaker to catch the drops, just a sheet of glass at the bottom and a long funnel of pitch above. This experiment also produced a famous drop in 2013, which was the one captured on video. It demonstrated beautifully that even the thickest, most resistant substances still move under gravity if you wait long enough. Both versions of the experiment have sparked broader conversations about the definition of solids and liquids. At what point does something that appears solid qualify as a liquid? Is time the only difference? The pitch drop forces us to reconsider our categories. Just because something doesn't appear to move doesn't mean it isn't. Sometimes motion is just too slow to see. And that's a profound idea, not just in science, but in life. The pitch drop is a metaphor for all the changes happening around and within us that we never notice in the moment. Geological shifts, evolutionary changes, the growth of a forest, the erosion of a coastline, the accumulation of knowledge, even the way we learn, think, and change as people. Much of a life's progress is imperceptible until suddenly something gives, and we realize how far we've come. That's part of why the pitch drop experiment holds such fascination. It's not just about fluid dynamics. It's about patience, endurance, and perspective. It's about slowing down and appreciating the processes that operate on time scales longer than a coffee break, a semester, or even a lifetime. Imagine a school child watching the live stream, knowing that the next drop might not fall until they're in college or retired. Imagine scientists a century from now still checking in on the same experiment, continuing to collect data, refining our understanding of viscosity. This is science that requires continuity, not urgency. It's not designed to solve a crisis. It's designed to stretch our sense of time. And maybe that's what makes it so strangely satisfying. There's no rush, no drama, just a quiet, gentle unfolding of nature's slowest truths. So the next time you feel like the world is moving too fast or that nothing is moving at all, think of that thick, glossy blob of pitch slowly inching its way downward through a funnel. It doesn't care about deadlines. It doesn't check its notifications. It just flows imperceptibly, relentlessly, and eventually, with all the drama of a sigh, it lets go. One drop closer to understanding. At first glance, an oak tree might not seem like much of a scientist. It doesn't wear a lab coat. It doesn't write research papers. It doesn't peer thoughtfully into a microscope or hold forth at international conferences. And yet, in a quiet, slow, and deeply persistent way, trees, particularly very old ones, are part of one of the longest-running natural experiments on Earth. They are living recorders, monitoring and responding to environmental change year after year, decade after decade, even century after century. Some trees live so long that they span the entire arc of human civilization. The oldest known individual tree, a Great Basin bristlecone pine in California, is over 800 years old. That means it was already a few saplings tall when the pyramids of Egypt were built, when writing was first developed in Mesopotamia, and when humans were just beginning to domesticate horses. That tree has been quietly conducting its own patient observation of the world through drought, fire, frost, and famine without ever leaving its spot in the rocky soil. Old trees are more than just impressive biological oddities. They're essential participants in a long-term ecological experiment that they didn't sign up for, but have contributed to with remarkable reliability. Because as trees grow, they keep a meticulous record of their experiences. Each ring in a tree's trunk tells a story, not just of age, but of the conditions under which that year's growth occurred. A wide ring might suggest a wet and sunny year full of resources and photosynthetic joy. A narrow ring might indicate stress, drought, disease, cold, or competition. This field of study, known as dendrochronology, uses tree rings as a scientific tool to reconstruct past climates and environmental changes. But when applied to ancient trees, especially those living in unbroken succession, it becomes something even grander. A natural experiment that can stretch back thousands of years and offer insights no human design study ever could. Let's take the bristlecone pines as an example. These gnarly, wind-twisted trees grow in harsh conditions, high altitudes, poor soil, extreme cold. It's precisely these rough surroundings that make them ideal record keepers. They grow slowly and conservatively, adding thin layers of wood even in the best of years. That makes their rings tight, distinct, and durable. In fact, some dead bristle cones preserved in the arid climate still have readable rings even after lying on the ground for thousands of years. By matching up overlapping ring patterns from living and dead trees, scientists can construct what's called a master chronology, a continuous ring record that goes back over 10 zeros, 0 years. That's longer than written history. It covers the rise and fall of empires, the migration of species, the warming and cooling of the earth, and even the eruptions of distant volcanoes. And what these trees have told us is astonishing. They've revealed periods of rapid climate shifts like the Little Ice Age and the medieval warm period. They've captured the fingerprint of volcanic eruptions, which can be seen as especially narrow rings following major blasts due to the cooling effects of volcanic ash in the atmosphere. And they've even helped calibrate radiocarbon dating, giving us a precise timeline to anchor archaeological discoveries. But the story doesn't stop with trees that are already ancient. Around the world, scientists are planting trees and monitoring existing forests as part of new long-term experiments designed to unfold over decades or centuries. These aren't flashy experiments with immediate payoffs. They're slow, deliberate efforts to understand how forests grow, how they respond to stress, and how they might adapt to a rapidly changing world. One such project is the Smithsonian's Forest Global Earth Observatory, or Forest Geo. It's a worldwide network of forest plots, some the size of small towns, where researchers tag, measure, and monitor every tree year after year. The data collected from these plots is used to study biodiversity, forest dynamics, and climate change. Some plots have been tracked for over 30 years, and the goal is to continue this work indefinitely. Why such long timelines? Because trees don't rush. A single generation might take a century to grow to maturity. Some species germinate only after fire or flood. Others may live for hundreds of years before dying naturally. If we want to understand how forests function and change, we can't just study them for a season or two. We have to stay for the long haul. Another example is the Harvard Forest in Massachusetts, where researchers have been studying forest succession since the early 20th century. They've watched how different species compete, how landscapes recover from logging or hurricanes, and how climate change is shifting the timing of leaf out and flowering. These observations are only possible through careful, consistent monitoring over decades, even beyond research plots. Trees are teaching us. Urban tree planting initiatives are increasingly being used not just to beautify cities, but to study the effects of greenery on human health, air quality, and temperature. Trees are being tagged with sensors that measure everything from sap flow to trunk expansion to carbon uptake. Each one is a mini laboratory recording data in real time and quietly participating in a global experiment on resilience, sustainability, and adaptation. And then there are the philosophical lessons. Trees remind us that not all experiments need to be fast or flashy to be meaningful. In a world obsessed with speed and instant results, they offer a different kind of wisdom, one that values patience, presence, and persistence. A tree doesn't grow by pushing harder or faster. It grows by quietly doing the work day by day, season by season, by responding to the light, the soil, the wind, by reaching upward and downward in equal measure. And this slow, steady growth can outlast empires. Think of the chestnut tree in Sicily that's been alive for more than 2,000 years. Or the ancient olive trees in the Mediterranean, some of which may have been planted before the birth of democracy. These aren't just trees. They're living links to the past, still growing, still observing. In a sense, every tree is part of an experiment in time. Not just how long a living organism can persist, but how it can adapt, store memory, and teach us things we never thought to ask. Can trees help us predict droughts? Can they warn us about changes in soil chemistry? Can they act as sentinels for air pollution or indicators of global warming? The answer, increasingly, is yes. Some researchers are even exploring the idea of tree phenology, the timing of events like flowering, leaf fall, and seed drop, as a biological calendar that responds to climate. By tracking these events across decades and continents, scientists can detect subtle shifts in seasonal patterns and ecological rhythms. And yes, trees even have a form of memory? Not memory in the conscious sense, of course, but a biological memory stored in the structure of their rings, in the distribution of their roots, in the way they respond to stresses based on past exposure. A tree that has experienced drought may adjust its future growth patterns, conserving water more efficiently the next time conditions get dry. In this way, trees aren't just passive participants in long-term experiments. They are active responders adapting in ways we're only beginning to understand. They are our slow-moving collaborators in the study of life. So, the next time you walk through a forest or pass a quiet street tree, pause for a moment. Consider that you are standing beside a scientist who's been working longer than you've been alive. A patient observer of the sky and soil, a recorder of history, a quiet participant in an experiment so slow and so profound that we can only see its outlines in hindsight. In their silence, trees are telling us something, not in numbers or graphs, but in rings and roots, in leaves and limbs, and we would do well to listen. In the rugged hills of England, nestled among sheep pastures and crumbling stone walls, a curious set of concrete blocks sits quietly, almost invisibly in the grass. There are no flashing lights or humming machinery, just simple blocks with names like North D, South A, East C. They don't look like much, but they are part of one of the world's most patient and determined scientific experiments. An experiment that has been quietly growing and occasionally decomposing since 1936. This is the park grass experiment, and it takes place at Rothamsted Research, an agricultural research station in Hertfordshire. Started over 80 years ago, it is the longest-running study of grassland ecosystems in the world. And what makes it extraordinary isn't just its longevity, but what it has taught us and continues to teach us about soil, nutrients, farming, biodiversity, and the delicate balance that keeps ecosystems ticking. The original question behind the experiment was simple enough. How does the addition of fertilizer affect the yield of hay? It was a practical problem. In the mid-19th century, agriculture was transforming, and scientists and farmers alike were hungry for data. How much ammonium sulfate should you add? What happens if you apply bone meal or potassium nitrate? And how does the land respond if you apply nothing at all? To find out, scientists marked off a field of grassland into plots and began treating each one differently. Some received no treatment at all. These became the control plots. Others were given different combinations of nitrogen, phosphorus, potassium, and lime. Each year they harvested the hay from each plot, weighed it, and recorded the results. Then they repeated the process the next year, and the year after that, and the year after that. The original researchers, Sir John Bennet Laws and Sir Henry Gilbert, probably didn't expect that their modest grass experiment would still be running nearly 2 centuries later. But the data kept accumulating, and soon it became clear that something remarkable was happening. The field wasn't just growing grass. It was growing a living record of how ecosystems respond to change. Over the decades, the park grass experiment has expanded far beyond hay yields. Scientists have used it to study species diversity, soil acidity, carbon storage, microbial life, and even the long-term effects of acid rain. By maintaining consistent treatments over many decades, the experiment has created a unique opportunity, a window into the slow-motion consequences of human intervention in nature. And some of the results have been surprising. One of the most famous findings is that the addition of fertilizer can reduce biodiversity. That might sound counterintuitive. You'd think that adding nutrients would make everything flourish, but in practice, it often allows a few fast-growing species to outcompete the others, leading to a less diverse plant community. Overall, on plots that received heavy nitrogen treatments, the once diverse mix of grasses and wild flowers gave way to a monoculture of aggressive species like Yorkshire fog and rough meadow grass. Meanwhile, untreated plots, those that received no fertilizer or minimal lime, retained a far richer array of plants, in some cases more than 40 species per square meter. That's an important lesson for land management and conservation. It shows that more isn't always better, and that nutrient enrichment, whether from fertilizers or pollution, can have long-term consequences for biodiversity. The park grass plots have also served as a kind of time capsule for studying environmental change. Because the plots have been so carefully managed and documented, scientists can detect even small shifts in soil chemistry and plant composition. For example, during the peak of industrial pollution in the mid-10th century, acid rain from coal-burning factories began affecting the pH of soils across the UK. But thanks to park grass, scientists could track those changes in real time. They saw how acid rain influenced soil acidity, how it affected plant growth, and how lime treatments helped buffer the effects. It became one of the first real-world demonstrations of acid rain's ecological impact and how long it can take for ecosystems to recover. Another fascinating aspect of the experiment is its ability to reveal the slow pace of soil change. You might think that adding lime or fertilizer would quickly alter the soil chemistry, but it turns out that the effects unfold over decades. In some cases, the soil in certain plots is still responding to treatments that were first applied more than 100 years ago. That's the kind of insight you can't get from a short-term study. Most modern experiments last a few years at most. Funding cycles are short, graduate students come and go, research priorities shift. But the park grass experiment continues patiently gathering data year after year, reminding us that nature doesn't always move at the pace of a research grant. And it's not just a relic. The experiment is constantly being adapted and expanded. Today, the plots are monitored with high-tech sensors, drone imaging, and DNA sequencing to study microbial communities in the soil. Scientists are using the data to model climate change scenarios, carbon sequestration, and the effects of changing land use. The graph may look ordinary, but it's part of a cutting-edge ecological observatory, an accidental time machine that lets us study the long-term consequences of decisions made before our grandparents were born. There's also something gently philosophical about the parkgrass experiment. It challenges our assumptions about what counts as progress or success or discovery. No one plot in the field is especially dramatic. There are no explosions or flashy results, just slow, steady change. A gradual unfolding of cause and effect. And yet, the insights gleaned from these quiet little rectangles of turf have shaped entire fields of science. They've informed agricultural policy, conservation strategies, and environmental regulations. They've helped us understand how ecosystems recover from stress and how fragile that recovery can be. They've shown us that soil is not just dirt under our feet, but a living, breathing, dynamic system with its own rhythms and memory. And they've done it all by growing grass. That might sound humble, but humility is one of the experiment's greatest strengths. It doesn't try to control the outcome. It just watches, records, and respects the slowness of nature's processes. In doing so, it offers a rare kind of wisdom, the understanding that not everything can or should be rushed. In an age of instant data and rapid feedback, there's something deeply grounding about an experiment that takes generations to complete. One that reminds us that science isn't just about answers. It's about observation, about patience, about showing up every year with a notebook, a scale, and a willingness to listen. The pot grass experiment is still listening. The grass still grows. The soil still shifts. The microbes still ripple and breathe. The seasons come and go, and with each harvest, a new line is added to the long, quiet story of how life responds to change. It's not glamorous, but it is glorious, because in the end, some of the most profound truths are revealed not by sudden breakthroughs, but by steady attention, by caring enough to keep going, by trusting that even the smallest observations measured in grams of hay or shifts in pH can illuminate the biggest questions. What happens when we intervene in nature? How do ecosystems remember? How long does recovery take? How much is too much? These are questions with no easy answers, but if we're patient and careful and willing to wait as long as it takes, the grass just might tell us. In the middle of a gently sloping field in Norfolk, England, beneath soil that has seen Roman sandals, medieval plows, and modern rubber boots, lies one of the most unusual time capsules in science. It isn't flashy or high-tech. In fact, it's a collection of glass bottles, hundreds of them, carefully buried in the earth. Each one contains a sample of soil and tiny seeds sealed away from the elements and waiting patiently for their moment. Not next week, not next year, but perhaps in the next century or even the one after that. This is the Seed Viability Experiment, and it holds a quietly profound place in the world of long-term science. It's not studying the stars or the structure of atoms. It's studying seeds, the tiny packets of life that lie dormant in the ground, waiting for the right moment to spring into action. And it's asking a deceptively simple question: how long can a seed wait? The idea began in 1879 when Professor William James Beal of Michigan State University decided to bury 20 bottles filled with a mixture of sand and seeds from 21 different plant species. Each bottle was sealed and buried upside down to keep out moisture. The plan was to dig up one bottle every 5 years, plant the seeds, and see how many would still sprout. At first glance, it may not seem like the kind of experiment that would change the world, but Beal understood something important. Dormancy is one of nature's most remarkable tricks. Some seeds can lie dormant for years, even decades before germinating. They wait for fire or rain or a shift in temperature. They wait through droughts and winters and centuries of soil accumulation. In a world of fast biology, photosynthesis, digestion, reproduction, seeds are the slow players. They are nature's patient optimists. The bee experiment set out to understand just how patient they could be. In the early years, the seeds behaved more or less as expected. After 5 years, many of the species still germinated well. After 10 years, a few began to fade. After 20 or 30, the drop-off was sharper. But here's the twist. Some species continued to grow far beyond anyone's expectations. After 50 years, a handful were still viable. After 100 years, astonishingly, a few still managed to sprout. As of the most recent exhumation in 2021, 142 years after burial, seeds from at least one species, Verbascam blaetaria, or moth mullen, was still capable of germinating. Let that sink in. These were seeds that had not seen sunlight since before the invention of the electric light bulb. They had waited patiently through 2 world wars, the moon landing, the invention of the internet. And still, when planted, they chose to grow. That kind of resilience is more than just a botanical curiosity. It speaks to the robustness of life itself, and it has practical implications for agriculture, ecology, and conservation. For example, understanding seed longevity can help with seed banking, the practice of preserving seeds for future use. This is a key tool in protecting biodiversity and ensuring food security in the face of climate change, habitat loss, and war. If seeds can be stored safely for centuries, they may serve as a genetic lifeline for future generations. The Beale experiment also helps us understand how plants can suddenly appear in landscapes where they haven't been seen in decades. If a forest is cleared or a fire sweeps through an area, seeds buried deep in the soil may seize the opportunity to germinate. These seed banks beneath our feet are a hidden archive of biodiversity, quietly holding potential futures in stasis. Other scientists have launched similar long-term studies. Some experiments focus on seeds stored in controlled environments, like the Spalba Global Seed Vault in Norway, a high-tech facility designed to preserve seeds from around the world against disaster. But there's something uniquely charming about Beale's low-tech approach. No climate control, no vaults, no robotic arms, just seeds, sand, glass, and earth. And of course, patience. The experiment schedule has been modified over the years. Originally, bottles were to be unearthed every 5 years. But as time went on and fewer seeds remained, the interval was extended to every 10 years, and then to every 20. The idea now is to preserve the remaining bottles for as long as possible, perhaps up to 3 centuries in total. That means the final bottle may not be opened until the year 2100 or beyond. And who will open it? That's the beautiful part. No one knows. The responsibility will pass down through generations of scientists, students, and caretakers. Each exhumation is an event coordinated in secrecy to avoid tampering, with a small team digging carefully through the soil to find a bottle that hasn't seen daylight in 100 years. It's like finding a message from the past, except instead of words, it's hope wrapped in cellulose. But it's not just the seeds that are waiting. The soil itself in those bottles is an archive. Future researchers may analyze it for microbes, pollen, grains, or isotopic signatures. They may uncover data that we never imagined collecting, 'cause the tools to do so hadn't yet been invented. This is one of the great strengths of long-term experiments, their capacity to outlive the limits of contemporary technology. They allow future generations to revisit old questions with new methods. What Beale started as a simple germination test could one day yield insights into climate history, microbial life, or genetic resilience, all from a dusty bottle of dirt. And the experiment has already inspired new ones. At Kew Gardens in London, the Millennium Seed Bank conducts extensive research into how different storage conditions affect seed longevity. NASA is studying seed behavior in space, testing whether seeds stored aboard the International Space Station retain their viability under microgravity and cosmic radiation. Agricultural scientists are experimenting with storing crop seeds under conditions that mimic extreme drought or heat, in hopes of future-proofing global food supplies. There's even a kind of poetic resistance in these studies. Seeds remind us that life has a backup plan, that even when everything above ground seems lost, something below may be waiting to begin again. And seeds are remarkably democratic in their resilience. Some of the toughest seeds come not from towering rainforest trees, but from weeds. Those scrappy, unwelcome guests in our gardens and cracks in the pavement. Moth mullein, the bee experiment surprise survivor, is a common roadside plant with a cheerful yellow flower and a reputation for growing where it's not wanted. But it turns out that resilience doesn't care about prestige. Life clings on wherever it can. In a way, the bee seed viability experiment is as much about humans as it is about plants. It's a quiet statement of faith in the future, an acknowledgement that even though we may not live to see the results, the act of asking a question and waiting for an answer is still worthwhile. It's a reminder that not all scientific discoveries come with immediate payoff, that sometimes the most important contributions are the ones we begin for someone else to finish. And that's a valuable message in today's world. When the news cycle moves in seconds and research funding is often judged by quarterly outcomes, there is deep wisdom in burying something in the soil and simply waiting. What if more science embraced that kind of patience? What if we invested in questions that would take 100 years to answer? What if we treated curiosity not as a sprint, but as a legacy? Because in the end, the Bayer experiment doesn't just measure seed viability. It measures scientific humility, the understanding that the world is vast, time is long, and not everything is meant to bloom today. So the next time you walk across a field or plant a seed in a pot, think about what might be waiting beneath the surface. Not just roots, but resilience. Not just potential, but history. Seeds don't ask for much. Just a little soil, a little light and time. Sometimes a lot of time. And when the next bottle is unearthed, perhaps by people not yet born, and those ancient seeds are given their chance to stretch and unfurl, it will be a quiet echo of a decision made long ago to plant questions and trust the future to harvest the answers. And so, as we reach the end of this long, meandering journey through the slowest corners of science, we return gently to the same quiet questions we asked at the beginning. What does it mean to observe with patience? What can we learn from experiments that take not hours or days, but decades, centuries, or even millennia to unfold? From drops of pitch falling once every 10 years to bacteria evolving over 0 generations to spacecraft quietly coasting beyond the solar system, we've seen that science is not always about rapid breakthroughs or flashy discoveries. Sometimes it's about showing up again and again to bear witness to the unfolding of time. Sometimes it's about planting a seed, literally or metaphorically, and stepping back. These experiments ask us to slow down, to pay attention, to trust that knowledge grows not just in the spark of a eureka, a moment, but in the long shadows cast by patient observation. Whether it's a grass plot that's been harvested since the age of steam, a starship drifting into interstellar night, or a handful of seeds waiting quietly in a buried bottle, these studies share a kind of quiet defiance. They defy haste. They defy forgetfulness. They whisper gently that some truths are revealed only when we're willing to wait. And maybe, just maybe, the most extraordinary thing about these long experiments isn't what they've discovered, but the kind of mindset they invite. One of humility, of curiosity, of care. So once again, we return to the original hope that this video wasn't too interesting, that it let your mind drift, your breath slow, and maybe helped you find rest. But if it did keep you awake, at least you've learned something, something soft and steady, something patient. Before you go, I'd love to know, where in the world are you listening from? What time is it there? Let me know in the comments below. And if you enjoyed this quiet exploration, please consider liking the video and subscribing to The Sleepy Scientist. There are always more stories waiting just beneath the surface, and just like a well-planted seed, we'll be here when the time is right.